This is part 2 of the walkthrough of the AQA GCSE Combined Science Chemistry 2023 Higher Tier Paper 1. Question 5. During electrolysis, ions are discharged at the electrodes to produce elements. A student investigates the electrolysis of sodium chloride. 5.1. Why does solid sodium chloride not conduct electricity? So, for something to conduct electricity, what is required is movement. And that will create a current. Now, if we're talking about movement specifically, we're thinking about two things. It could be electrons or it could be ions. But if it's solid sodium chloride, remember that solid sodium chloride will be an ionic compound and its structure will be a lattice. This means that the ions, because sodium chloride is ionic bonding that's involved, the ions are not going to be able to move. If they're not really able to move, then a current can't be generated. So that would be the reason that the ions are not free to move. (5.2) Sodium chloride solution conducts electricity. Complete the sentence. Sodium chloride also conducts electricity when blank. Well, it tells us that it's a solution. So that means that something has dissolved in water. So we can't use the phrase dissolved because that has already been explained to us. So what would be the other reason in which sodium chloride can conduct electricity? Well, it would be when it is a liquid. And the reason why sodium chloride could be a liquid is because it's been heated. So when it's a liquid, it would be an acceptable answer. But when sodium chloride is heated as a solid, that's known as molten. So either liquid or molten would be an acceptable answer. Figure 5 shows the apparatus for the electrolysis of sodium chloride solution. So here is our setup. We've got a power supply, and then through wires, it's connected to two inert electrodes, which is placed in a beaker containing sodium chloride solution. Reminding ourselves that this word inert means unreactive. So being placed in the sodium chloride solution means the electrodes will not react. 5.3. Suggest an element that could be used to make the inert electrodes. Well, it's got to be something that, as I said, will not react with the sodium chloride solution. Now, if you have done an electrolysis setup similar to this before, for example in your required practical, then the electrodes that you probably would have used would be made from carbon. Now that is an element that won't react with anything in the solution, so that would be appropriate. Remember also that carbon can be used to make certain molecules, specifically giant covalent molecules. So a giant covalent molecule that will contain carbon that could be used would be graphite. (5.4) Complete the half equation for the production of chlorine at the positive electrode. So from our setup, it's telling us what we're going to be forming at the positive electrode. So at this positive electrode, we should be forming chlorine. Now, if that's what we're producing, that's got to be on the right-hand side of our equation, so we should already be able to write chlorine in our product. Now, if it's a half equation, then what we have to be showing in our equation is either oxidation or reduction. Now remember that these two reactions involve the transfer of electrons. Remember, our oil rig mnemonic can help us with this. Oxidation is loss and reduction is gain, but it's speaking in terms of electrons. So in the case of Cl-, this is our chloride ion, so that means it's got an extra electron. When it becomes chlorine, this is meant then that the chloride ion has lost an electron to become chlorine, and that is oxidation. So we need to show that this chlorine has lost electrons, and we do that by using an E- symbol there. The final thing that we need to do now, remember, it is an equation, so every equation needs to be balanced, so we need to make sure that both sides have the same number of chlorine atoms and electrons. So you can see that we've got 2 chlorine atoms on our product side. So we need to show that by putting a 2 in front of chloride. However, because we put a 2 in front of this chloride now, what that essentially means is that we have 2 atoms with 2 electrons. So we would need to then show that 2 electrons have been lost from these chlorine atoms, and that is by putting a 2 in front of the electrons. (5.5) Sodium chloride solution has a pH of 7. During the electrolysis of sodium chloride solution, hydrogen gas is produced at the negative electrode. The pH of the solution increases. Explain why. 4 marks. So let's look at each point carefully in our question. The sodium chloride solution has a pH of 7. So from our previous questions, we remember that is neutral. Hydrogen gas is produced at the negative electrode, and the pH of the solution increases. So that means that it's greater than 7. So let's go back to our diagram. Just kind of annotate this a bit now. So remember, we formed chlorine gas at the positive electrode. At the negative electrode, we're forming hydrogen gas. Now, if we're forming hydrogen gas at the negative electrode, this means that the reaction has involved reduction, which we said is the gain of electrons. So that means now that we actually started off with hydrogen ions, which have then gained electrons to become hydrogen gas. So that can be something that we can include in our answer then. We can mention that hydrogen ions have been reduced. Now, for these hydrogen ions to have been reduced, it must mean that they have been attracted to the negative electrode. Remember, they're positive, the ions, and the negative electrode, they are opposite, so that's going to cause some attraction. Now, what was going to happen next? Well, we have to also think that we've got another ion in this setup which is positive. A reminder that in the beaker we've got our sodium chloride solution. Remember in electrolysis that this would be the electrolyte. So from this sodium chloride solution we'd get the ions which are free to move, and the ions would be Na+, sodium ions, and the chloride ions. So we've dealt with the chloride ions already. We know what's happening there because it told us we're going to form chlorine. But we've also got sodium ions. So the sodium ions could be attracted to the negative electrode too. But as they've told us in the question, only hydrogen gas is being produced. So there must be a reason why hydrogen gas is produced as opposed to sodium being produced at the negative electrode. Well, the reason is due to the reactivity series. And because in our reactivity series, hydrogen is lower in its position than sodium, that means it's less reactive. So due to the fact that it's less reactive, it is the thing that gets produced at the negative electrode. So you want to say then that hydrogen is less reactive than sodium. So if the chlorine gas produced at the positive electrode, if there's hydrogen gas produced at the negative electrode, inside our beaker, we have got then sodium ions which are free. But why is that leading to an increase in the pH? Well, it's about this term solution. Now, if it's a solution means that something has dissolved in water. So, what has actually happened then is that the sodium chloride has dissolved in water and then has split into the sodium and chloride ions. We know what's happened to the chloride ions. We've got the sodium ions that's left in the solution. But what about the water itself? Well, the water, that becomes split also. So what ions are coming from water now? Well, there are two, hydrogen ions and the hydroxide ions. There will be an equal number of both of these ions from one water molecule. So from all the water molecules, we generate an equal number of protons, hydrogen ions, and hydroxide ions. But one more time, we know what's happening to these hydrogen ions. They go through reduction and become hydrogen gas at the negative electrode. But what about this hydroxide ions? Well, what will happen then is the sodium ions and the hydroxide ions, those two will combine and they will produce sodium hydroxide. And sodium hydroxide is an alkaline solution. And remember that alkaline solutions will have a pH that's greater than 7. So our last 2 points that we would need to say then would be that the water molecules split to form hydrogen and hydroxide ions. And due to the hydrogen ions being reduced, there'll be a decrease in the number of hydrogen ions, and therefore that will lead to an increase in the pH. There we've addressed both of the bullet points in the answer. I should be getting off 4 marks. Question 6. Acids react with some metals to produce soluble salts. A student adds magnesium to hydrochloric acid until no more acid reacts and excess magnesium remains. The equation for the reaction is shown. 6.1. Describe how solid magnesium chloride is obtained from the reaction mixture. So again, this is similar to one of your required practicals where you're dealing with the process of crystallization. Now, during crystallization, what happens is you take a base and then you add that to an acid. You'll add as much of the base as possible until no more of the base can react. So that's what we mean by excess. And then you will filter that mixture so you are separating what has reacted from what has not reacted. And then you heat the mixture using a Bunsen burner in an evaporating basin until all the water has been removed. And then you leave it to cool, and then eventually solid crystals will form. So this is extremely similar. So we just need to describe a little bit what's going to happen. So using the information in the question, they specifically told us solid magnesium chloride. So based on my description, the only time that we would get solid magnesium chloride is at the end, where we've got the crystals forming due to the process of crystallization. So that would be the process that needs to be mentioned. Crystallization is the process. But what must happen first? We need to make sure the key step is that we filter our reaction mixture from this excess magnesium that has been added. (6.2) The reaction between magnesium and hydrochloric acid is a redox reaction. Explain what happens to the magnesium atoms in this reaction. So let's return to the equation. We are focusing on the magnesium atoms. Now, redox is a combination of reduction and oxidation. So that must mean that within that equation, both of those processes are happening. But they're not happening to the same atom, they're happening to different ones. So what we need to do is look at our equation and then figure out what one is happening for magnesium in this case. Well, remember from before, metals always form positive ions. So in our equation, the magnesium is the metal. In the product, we have magnesium chloride, ionic compound, because there's a metal and there's a non-metal. So in our magnesium reactant, our atom, the charge on this would be 0. In the magnesium ion, in the ionic compound, it would be positive. So if it's positive, That must mean that it's lost electrons to become positive. So again, using the oil rig mnemonic, that must mean that oxidation has taken place. So we can say that oxidation has occurred to the magnesium atoms. But if we look a little bit closely now, there are 2 chlorine atoms in magnesium chloride. Magnesium itself is in group 2 in the periodic table. So that means in its outer shell, it's got 2 electrons. So for it to have a full outer shell, it would need to lose 2 electrons. So specifically then, this oxidation has caused magnesium to lose 2 electrons. (6.3) 0.72 grams of magnesium is added to 100 centimeter cubed of hydrochloric acid. The hydrochloric acid is in excess. Calculate the concentration of the magnesium chloride solution produced in grams per decimeter cubed. The relative atomic mass of magnesium is given. The relative formula mass of magnesium chloride is given. 6 marks. So they've given us the mass of magnesium and the volume of hydrochloric acid in which this magnesium has been dissolved in. We want to find the concentration, but of magnesium chloride. So we should expect to use both the mass of magnesium and the volume of hydrochloric acid in our calculation. Now, what we would need to do in this question is we'd need to use our knowledge of reacting masses. And within our knowledge of reacting masses, we need to do a few things. We need to find the moles of our substance that we're focusing on, and we need to find the molar ratio between something in our reactants and something in our products for us to continue. But remember, we also need to actually find the concentration of a solution. And if it says in grams per decimeter cubed, then just like in our previous question, we need to use the formula mass divided by volume. So where can we start? We can start by finding the number of moles of magnesium. So which equation can we use that includes moles? It is mass divided by the RFM. But remember, we're dealing with magnesium here, so it'd be the relative atomic mass of magnesium. So our mass is 0.72 grams. We're then going to divide that by 24, which is the relative atomic mass of magnesium, and we get 0.03 moles of magnesium. Now, let's take our equation and write that just underneath so we can remind ourselves of everything instead of going up and down. Now, we have figured out now that there is 0.03 moles of magnesium. Remember that we're focusing on finding the concentration of magnesium chloride. Now, for us to find the concentration of magnesium chloride in grams per decimeter cubed, we would need the number of moles of magnesium chloride, and then we would need the mass of magnesium chloride. So what then would be our moles of magnesium chloride? Well, from our reacting masses, we need to use a Euler ratio. We can see that there are no numbers in front of magnesium and in front of magnesium chloride. So that means that the proportion would be 1 to 1. So if we've got 1 mole of magnesium, we'll have 1 mole of magnesium chloride. But we know actually we've got 0.03 moles of magnesium, so that means that we've got 0.03 moles of magnesium chloride. So what we can do now is we're able to find the mass of magnesium chloride. Now the mass of magnesium chloride, we can use our equation for moles and rearrange it. But this time we're not using relative atomic mass because it's a compound. We're using the relative formula mass, which is given to us in the question. So to find the mass, that would be number of moles multiplied by the relative formula mass. And number of moles, as we just said, is 0.03, and we're going to multiply that by 95. And if we do that, we get a mass of 2.85 grams. So this will be our mass of magnesium chloride. But what's our volume? Well, the volume in our question, we've got 100 centimeter cubed of hydrochloric acid. So that will be our total volume that we have gotten here. That's in centimeter cubed. Our final answer of our concentration needs to be in decimeter cubed. So again, we're converting between centimeter cubed to decimeter cubed. To do that, we need to divide by 1000. So 100 centimeter cubed divided by 1000 will be 0.1 decimeter cubed. So finally, to find the concentration, so our equation at the top, mass divided by volume. Our mass is 2.85 grams. Our volume is 0.1 decimeter cubed. And that will give us a final answer of 28.5 grams per decimeter cubed. Question 7. This question is about structure and properties. Question point 1. Which pair of substances both contain atoms in hexagonal rings? So let's go through our list and check. Diamond does not have hexagonal rings because each carbon atom is covalently bonded to 4 other atoms. So it cannot be diamond and graphite. If we check our graphite, remind ourselves of that knowledge, that is contained in hexagonal rings. Right? Because diamond does not, that cannot be the answer. Graphene and fullerenes. Well, graphene is a single layer of graphite, so that would have hexagonal rings. Our fullerenes, well, our fullerenes exist in multiple configurations, one of them being Buckminster fullerene, and that actually does have hexagonal rings. So our graphene would be the answer. Silica, just to check, silica has a similar structure to diamond, so it's covalently bonded to 4 atoms, so that wouldn't be correct. So that rules out the bottom one. 7.2. Explain why the structure of copper allows the conduction of thermal energy. Well, copper is a metal. If it's a metal, then it will contain metallic bonding. And what can you remember about metallic bonding? Well, metallic bonding, one of the features of it is you have positive metal ions surrounded by a sea of delocalized electrons. Now we're talking about conduction of thermal energy. Conduction, movement. So similar to our question with electrolysis and how sodium chloride can conduct electricity when it's liquid or in a solution, it's because something is able to move. In the case of our metallic bonding, what is able to move is the delocalized electrons. So in this case, what are the delocalized electrons able to move through? They're able to move throughout the whole structure of this copper. Now, what are they going to be doing as they move through the whole structure? Well, as they move, they can carry and transfer the energy from one place to the other. .3. Explain why copper oxide has a high melting point. Let's start with high melting point. What does this mean? Well, melting point is the temperature at which a solid turns into a liquid. For a solid to turn into a liquid, energy must be provided. So if it's a high melting point, then that means a lot of energy is required. But what is it required to do? Well, copper oxide now. Copper oxide is an ionic compound. Copper has a positive charge because it's a metal. Oxygen has a negative charge because it's a non-metal. So the ionic bonding now is through an electrostatic force of attraction. But if you want to separate an ionic compound, which is what would happen when it's melting, you would need to overcome those forces of attraction. But if a lot of energy is required, then that must mean that those electrostatic forces of attraction are strong. So, what's a lot of energy required to do? Is to break the electrostatic forces of attraction, which are strong. Now, again, let's just be clear when we're in our explanation. What is the reason why there is an electrostatic force of attraction? It's due to the presence of oppositely charged ions. Copper positive, oxygen negative. So, for our 3 marks here, we're stating that there are oppositely charged ions. We're stating that there are strong electrostatic forces of attraction. And then our third point is that a lot of energy is required to break those strong forces. 7.4. Explain why water, H2O, has a low melting point. Well, it's almost the opposite to the previous question. What's similar is that we're talking about melting point. So, it's again thinking about energy. But this time they said it's low. So instead of a lot of energy required, it's a little amount of energy required. How is it different though? Well, water is not an ionic compound now. It's a covalent compound. And if it's a covalent compound, there are also going to be another type of force. And this time it's not electrostatic because there's no charges. It's going to be intermolecular. So here are two water molecules. Between the oxygen and the hydrogen atom, because they're sharing electrons, this is the covalent bond. But between the water molecules itself, this is the intermolecular force. So what we need to say then is a little amount of energy is required to break these intermolecular forces. But if a little amount of energy is required, then they're not strong, they're weak. So let's state that first. A little amount of energy is required to break the intermolecular forces. Now, where's our third point going to come from? Now, our copper oxide, as we mentioned before, is ionic, but structurally, just like sodium chloride, is going to be in a lattice structure. So that's going to be quite large. So again, would lead to the explanation of a lot of energy needed. But our water molecules, these now are actually small molecules. So that would explain why the forces are weak, because there's not a lot of them.